The air at Apple Park crackled with anticipation, but nowhere was the energy more palpable than during the deep dive into Swift concurrency. For years, concurrency has been the twin-edged sword of software development, promising unparalleled performance and responsiveness, yet fraught with the peril of data races and arcane complexities. WWDC 2025 unveiled a conceptual leap, a refined philosophy for Swift concurrency that promises to transform this challenging domain into an accessible, intuitive, and fundamentally safer experience for developers. The core message resonating from the session was a profound shift in default behavior, a direct response to the invaluable feedback from the Swift community. While Swift 6 bravely ushered in compile-time data race safety, its eagerness to implicitly offload work, even when parallelism wasn't explicitly sought, sometimes led to a barrage of compiler errors, forcing developers to wrestle with concurrency primitives sooner than necessary. Swift 6.2, showcased as the engine of this new era, elegantly sidesteps this by championing a single-threaded until proven parallel philosophy. This isn't a retreat from concurrency's power, but rather a strategic repositioning. The most natural, straightforward code developers write will now, by default, remain on a single thread, inherently free from the specter of data races. Concurrency is no longer an implicit assumption but an explicit choice, made when the performance demands truly warrant it. A cornerstone of this renewed clarity is how async functions behave. Previously, their execution context could be a source of subtle races. Now, an async function not explicitly tied to a specific actor will seamlessly continue execution within the actor from which it was called. This simple yet profound change drastically reduces the mental overhead of tracking execution contexts, eliminating a common class of data races by default. Further bolstering this paradigm is the introduction of isolated conformances. This elegant solution empowers types primarily living on the main actor to conform to protocols without compromising the integrity of their main thread-bound state. The compiler itself becomes the vigilant guardian, ensuring that protocol witness implementations respect the main actor's sanctity. And for applications where the UI reigns supreme, an opt-in mode to infer the main actor by default for entire modules was met with enthusiastic applause. This drastically curtails the need for explicit at-main actor annotations in predominantly single-threaded UI code, allowing developers to focus on application logic rather than concurrency boilerplate. But what happens when the call for parallel processing becomes undeniable? When CPU-intensive tasks genuinely need to be unshackled from the main thread to maintain a fluid user experience. Swift 6.2 doesn't just make single-threading easier. It makes the deliberate introduction of concurrency safer and more predictable. The new concurrent attribute serves as a clear signal. Functions marked with it are destined for the concurrent thread pool, liberating the calling actor to continue its own work simultaneously. This explicit demarcation ensures that developers are consciously engaging with parallelism, armed with the compiler's full support. The journey into concurrent programming, as envisioned by Swift 6.2, is a graduated one. Most applications, the presenters emphasized, can thrive for a long time, or even indefinitely, on a single main thread. The main actor, representing this main thread and its data, becomes the default sanctuary. Swift's protections ensure that code and data isolated to the main actor are shielded from concurrent access conflicts, as there is, by definition, no concurrency within the main actor itself. The first step beyond this sanctuary is typically driven by the need to handle high-latency operations, like network requests or disk I/O, without freezing the UI. This is where asynchronous tasks come into play. By marking a function async and using a wait at points of potential suspension, like waiting for a network response, the function can pause its execution on the current thread, allowing other work, particularly UI updates, to proceed. Crucially, this often doesn't even require introducing true parallelism into your own application code. Many library APIs, like URL session, intelligently offload their work to background threads on your behalf. Your code simply adopts async/await to remain responsive. Multiple such asynchronous tasks can interleave their work on the main thread, each task progressing in order, taking turns, maximizing resource utilization without the complexities of true multithreading. The need for true concurrency arises when computations themselves, not just waiting, become a bottleneck on the main thread. Profiling tools might reveal that a specific operation, like image decoding, is consistently causing UI stutters. This is the signal to deliberately move work to a background thread. Applying the @concurrent attribute to a function like decode image instructs Swift to execute it on the system's concurrent thread pool. This pool is a dynamic resource, its size adapting to the device's capabilities. A task running on this pool might suspend and resume on different physical threads, all managed transparently by the system. This transition, however, immediately brings up the critical question of data sharing. How does data flow between the main actor and these concurrent functions without inviting chaos? Here, Swift's sendable protocol is the linchpin. Sendable types are those whose values can be safely copied or transferred across concurrency domains. Value types, structs, enums, basic types like string and int, and collections of sendable types are often inherently sendable because passing them creates independent copies, eliminating shared mutable state. Classes and closures, being reference types, present a greater challenge. They are not sendable by default if they encapsulate mutable state that could be modified concurrently. Swift's compiler rigorously checks sendable conformance at every boundary where data crosses between actors or tasks. If a non-sendable type is captured by a concurrent task, the compiler flags it, preventing a potential data race before it ever runs. The guiding principle becomes: modify data before sending it to a concurrent context, or ensure that access to shared mutable state is properly synchronized, often by moving that state into an actor. And this leads to the final stage in the conceptual journey: custom actors. As an application grows, the main actor can become overburdened with managing too much disparate state, for example, network managers, data caches. When tasks frequently need to check in with the main actor for data not directly related to UI, it can create contention. Custom actors offer a way to decentralize this. An actor type, much like a class, encapsulates its own state. However, an actor guarantees that only one task can access its mutable state at a time, even if multiple tasks are trying to call its methods concurrently. Actors themselves are sendable, so they can be freely passed around. Unlike the singular main actor, you can create many instances of custom actors, each managing its own domain of data, running on the concurrent thread pool, and thereby offloading work from the main thread. The WWDC 2025 presentation on Swift concurrency was not just about new features, it was about a refined vision. It's a vision where the path from simple, single-threaded applications to complex and highly concurrent systems is paved with clarity, safety, and progressive disclosure of complexity. By defaulting to simplicity and making the introduction of concurrency an explicit, compiler-assisted step, Swift aims to empower all developers to build more responsive and powerful applications without fear of the data race. The journey is clear: start single-threaded, introduce asynchrony for latency, embrace concurrency for performance, and leverage actors for robust state isolation. The future of Swift concurrency, it seems, is not just powerful, but profoundly approachable. Swift 6.2's concurrency enhancements empower developers to build faster, safer iOS apps. With WWDC 2025's tools, now's the time to dive in. That's it for this episode of Byte Chronicles. Like, share, subscribe, and we'll catch up in the next one.